In this video, we're going to be graphing exponential functions. I'm going to spend most of my time in Desmos to graph these functions. Part A, we're going to look at f of x is equal to 2 to the power of x, and then we're going to look at g of x is equal to 4 to the power of x. Okay, let's hop over to Desmos, and I'm going to spend the rest of the video in here. So we're going to graph y is equal to 2 to the power of x, and normally the way I would graph this, I take x values and substitute them into the equation for x, and you could see how to do that in a prior video. Now, I've created a table in Desmos, so you could see right here on the screen, those are the points that we get when we substitute x is -3 through x is 3 into the function y equals 2 to the power of x. So we have a bunch of points that we've plotted, and we would connect those with a smooth line. And here you have a classic exponential function that has a horizontal asymptote at y equals 0. You can see that this function is riding along the x-axis as it goes to the left, and it is increasing all of the time. It has a y-intercept of 0, 1. This graph does not have any x-intercepts. Okay, it never crosses the x-axis. Its domain is all real numbers, so any number to the left, any number to the right will work as an input, and the range is any number greater than 0. So we never get negative numbers from this particular function. Now, we're going to graph y equals 4 to the power of x. So now our base has increased. And let's just take a look at what happens. So I plug in the same x values. I'm going to zoom out a little bit. Plug in the same x values, and I'm going to connect them with a smooth curve. And you can see what happens when we increase that base from the first function with a base of 2 to the second function with a base of 4. This exponential function is now increasing much faster if you're looking to the right of the y-axis. It's increasing much faster than the original function in red. But when you zoom in, you can see that to the left of the y-axis, those y values get smaller faster as you're moving to the left. And the reason is when you're plugging in negative values into an exponential function, those negative values make the value of your function a fraction. And just as a reminder, I'll just plug in, say, when x is -3. If you plug that into the first function, 2 to the power of -3 means 1 over 2 to the power of 3, which is 1 over 8. When we do the same thing for the second function, 4 to the power of -3, we get 1 over 4 to the power of 3, which is 1 over 64. So you can see the second function, those values are much smaller than the values of the first function. Okay, let's shut those off, and let's take a look at the next two. Now our first function is y equals 2 to the power of -x. Again, I plug in my x values, and I have arbitrarily chose -3 to 3. I like to choose some negative values, 0, and some positive values. And they're nice and small, so they were easy to work with. I plot my points, and I connect them with a smooth line. And here you can see now the function is decreasing. It still has a horizontal asymptote at 0 as y equals 2 to the power of x did. The domain is still all real numbers. We still have a y-intercept at 0, 1. There are still no x-intercepts for this function since it does not cross the x-axis. and the range is any number greater than 0. Let's look at the next function, y equals 4 to the power of negative x. So we have our points, we connect it with a smooth curve, and here you can see that when the base is increased, this function is decreasing much faster when we're looking at the graph from left to right. So just a couple of things. Let me shut these points off. I'm just going to look at the functions themselves. When the exponent was negative, we have a decreasing exponential function. We generally call that a decay function, okay, if we have an exponential function that's decreasing. When the exponent was positive, let's try to get these turned on. Okay, when the exponent was positive, we had an increasing exponential function, often called a growth function. So there are our two growth functions. There are our two decay functions. Okay, let's just jump down and let's look at a couple of transformations. So we're going to look at transformations of 3 to the power of x. So this is our original function. You can think of this as our parent function, 3 to the power of x. What happens when we add 1 in the exponent? Okay, you can see that this function moves 1 to the left. If you're just tracking this point 0, 1, it is now over here on our red function here. It is now at negative 1, 1. It has moved 1 unit to the left. So when we're adding or subtracting in the exponent, that's inside our function. So if we're adding, the function moves to the left. If we were subtracting, our function would move to the right. Now the next one, 3 to the power of x minus 2. So now we're subtracting 2 outside our function. And you can see our function shifts down. So if we're subtracting outside our function, the function shifts down. If we were adding, it would shift up. Let's look what happens when we have a negative sign out in front of this function, negative 3 to the power of x. Okay, just like all the functions that we've looked at, when there's a leading negative, it's reflected over the x-axis. You can see that happening right there. And then finally, our last one, 3 to the power of negative x. So there's a negative sign inside our function, and similar to the two functions we looked at earlier, this is reflected over the y-axis. Okay, so you've learned how to graph exponential functions, and we've looked at several transformations in this video. If you have any questions, you should refer to this video. And remember,